Yes, live started, sir.
Yeah. So, good morning, everyone. So, this is again the live interaction for the NPTEL course, Interfacial Fluid Mechanics. All right, I can see Himanshu has joined. Yeah, the live interaction is also being posted on YouTube. So, Himanshu, go ahead if you have any questions. Which week material have you covered?
Sir, till week 9 we have done.
Okay. Week 9 is rupture of thin films.
Yes, sir. It is rupture of thin films.
Okay. Okay.
I have some clarifications to ask from week 9. Sir, the lecture 1, equation J where you derived. So, if you could share the screen there, equation J.
I will do that. I'm a little better prepared this time. So I have basically logged into my Zoom as well. So let me do that. Yeah. Is this the correct one we're looking at?
Yes, sir. Here's the equation J, sir. Where we derive the most important equation which we have used in the subsequent lectures, sir, which is del H by del T equals to del X by del X. And that's H by 3, H expressed.
Equation J. I have not labeled it in this particular equation, in this particular lecture. So I don't know which one.
Sir, I think it's the second lecture, sir. Sorry, I missed it.
Okay, I'm right there. Yes.
Yes, sir. Yes, sir. Sir, here in the just line above where we write substituting, and just below that, sir, if we put the, I was deriving this, and I don't know whether I missed it. I mean, I've done something wrong, but in the in the line that we have written substituting, so now we see that relation on the kind. It's just above, sir. Just above. Yes, sir. Here in the kinematic conditions, sir, where you have written. So where when we put this, there is, sir. I mean, I'm not getting the same answer. So in this line, I think there is a there's a mistake that either I have done or maybe some problem is there. So, del square p by del x square, sir, this line.
Okay, let me just. Okay, so here, so this is the kinematic condition. The kinematic condition basically relates the velocities to the interface position. Okay, right? And we have basically used Leibniz's theorem, Leibniz's rule, to evaluate del U by del X, del U 0 by del X. That's the leading order velocity gradient in the horizontal, velocity variations in the horizontal direction. So that's when the U is a parabola. And then we have basically taken the derivative using, so is this term okay? Integral of 0 to H.
Till here it is okay. Yes, sir, till here it is okay. It is the error is coming on the second last line or before the equation.
Give me a second. Is this okay? This step, is it okay?
This till here it's okay. Till here it's okay.
Okay. So now substituting this in the kinematic condition, we get. So all right. Okay. So what have we done here? You just simply substituted it over here. U
पे क्लिक करो, ब्लू बोल रहा है क्लिक करो, नहीं पूछ रहा है ना वो ब्लू कलर का है।
Can I have, there is some disturbance. Yeah, okay. I see more participants this week. It's good to see that. Okay. So have you ensured that this quantity is evaluated, Himanshu? Have you ensured that this quantity is evaluated at y equal to h?
Yes, sir. When we put this at y equals to h, sir, sir
This
only
is
then,
x,
sir.
this is
Yes,
x square by 2. This is x square by 2. You have made sure of that, right?
yes, sir. Yes, sir.
Okay, so this is so far is okay. Give me a second.
Sir, when we do that, when we put y equals to h in this line, so just below we have written just below which we have written substituting. So del square p by del x square. This term, if we put y equals
No.
to h, then this will become h square by 2. The
No, I
So
understand, but Himanshu, I'm just saying, I'm just trying to see this. Okay, this is the expression of u. Okay, that's the expression for u, velocity. It's a parabolic velocity profile. Okay,
yes, sir.
right, and that's what is over here. I'm just trying to connect this equation here, the kinematic condition, the equation over that I'm highlighting here. I'm connecting this to the equation here, and I don't see anything wrong so far. I don't see any algebraic mistakes.
But sir, here, sir, if you put h, sir, if you put y equals to h here in this where you have highlighted the blue color, this blue color. So if you put y equals to h, then there will be no term which will be, sir. Then I mean, h square by 2 term is not should not come actually.
Second term and fourth term will be cancelled out, sir. If we kept
Yes, sir.
y.
Which one?
Second
Sorry,
term,
can I? Which term should cancel out again, guys?
second term and fourth term will be cancelled out, sir. If we kept y equal to h.
Second term as in this term.
Yes, sir, that term.
Okay, and the fourth term essentially reduces to h square by 2 minus h square. That is minus h square by 2.
Yes,
Okay, this is h square by 2 times hx.
yes, sir.
Okay, so minus x square by 2 times hx times del p by del x. So this essentially whole thing becomes the second term. I'm just trying to evaluate the second term. Let's do that quickly over here. Okay. So let me do that again. Oh, sometimes okay, I think it's easier for me to just delete this and do it again. Sorry. Okay, so now let's quickly check this again. So that is d square del square p0 by del x square into minus h cubed by 3. This becomes plus del p0 by del x into x square by 2 times hx plus del h by del t. Okay, I can see that issue. Minus del p0 by del x times h square by 2 hx, correct?
Yes, sir.
And what we seem to be doing is saying this. Okay, that's interesting. What I seem to have done is I've added them up. Huh? No, I've not
Sir,
even added them up. Sorry.
Sir, I did take the step above. So till here I was getting the same, and just after this, the change it came.
Okay. Okay. So. Okay. Let me just. Give me a few minutes.
But the dispersion relation is correct, sir. After substituting the perturbation, the dispersion equation that we are getting is correct, sir. After getting into the linear PDE, we get the same dispersion relation, sir.
Okay. Okay. At least that's good to know. But I'm just trying to find out why where has the mistake arising. So just follow. If I just continue here, I simply get del square p0 by del x square times h cubed by 3 with a minus sign plus del ht by del h by del t is 0. So this simply gives me del h by del t is equal to h cubed by 3. Well, this is not the pencil equation. That is for sure. This is definitely wrong, I know for sure. I'm trying to see, it's okay. I'm trying to trace my steps back and see where the mistake could have come from. So equation B here, equation B is going to give me the velocity profile. Okay. If I integrate equation B twice, the first term I get is del P by del X times Y. The second time integrated, I get y square by 2. That's how I get a parabolic velocity profile. So that would be, that is exactly done in this green colored text. All right. So far, okay. Now, we integrate equation C to get the pressure variation along the thin film with an arbitrary constant of integration. The arbitrary constant of integration C1 is determined from the normal stress balance, which is equation F. So it says that the pressure inside the thin film minus the pressure outside on either side of the interface is equal to the normalized curvature. Okay, that is minus epsilon cubed by Capelli number times HXX. So, and this is done at the interface. So over here, I can see this follows the pressure inside. And minus pressure outside. And this gives me the expression for C1. That looks okay to me. And now once I know C1, I can evaluate the hydrostatic pressure P0 inside the thin film. Basically, P0 is a function of X and Y because Y variation is coming from this Y minus H term, and X dependence is coming from the dependence of height on X. Okay. So now that I have equation H, Why do we need equation H? Equation H essentially can be substituted back into equation B, or rather into the velocity profile. Okay. So velocity profile involves del P over del X. And epsilon cube L square rho G1 mu naught Hx. Del P over del X also looks okay to me. So this is the continuity equation that I'm integrating. Right? The continuity equation. Okay, this looks okay. Now using equation E. Equation E is the kinematic condition, I believe. Yeah. At the interface. I was here.
Sir, there is one thing I wanted to say.
Yeah, go ahead. I think
Sir,
I've noticed the mistake, but yeah.
Sir, till that point, just before that equation, where we put the equation J, I've got the same expression. I mean, just before that equation J, I've got the same but just when we say that was cancelling out for me, and that is only where the discrepancy came.
I couldn't really understand you, Himanshu. It was a little challenging to understand. Could you repeat that again?
Sir, I was just saying that till just before equation J, I was getting the same point, same equation I was getting, but mine was cancelling out h square by that part was cancelling out square by 2. That was the only change I had. But before that, same equation I had.
So
Sir, one more thing, just to mention that Leibniz rule does contain derivatives of the boundary terms also. So there is one term in Leibniz rule which comes about del b by, so del b by del t term should come there, because in Leibniz rule there is one boundary differential terms also.
That's the only place where I could have. uh, yeah, but yeah, usually when you write down the full rule will be something like this. Well, I'm trying to see if I can squeeze it here. Let's say squeeze it in here. The full rule, if I follow the same color thing, then I have a d by ds. I'll write it for d by ds in this case. All right, are you able to see this? Okay. So I have d by ds integral a to b f of, let's say, s comma t dt. This would be integral. Okay, I think I think there's a mistake in the boundary. I missed the boundary term. So you have here a is a function of here a and b can be functions of s. Okay, a of s to b of s, partial derivative with respect to s, f of s comma t dt. That's the boundary term. Sorry, that's the integral. Plus, I have two boundary terms. So first would be s comma b of s times d by ds of b of s minus f of s comma a of s d by ds of a of s. Is that fully visible? I hope it's not getting cropped. Okay. Now we have this. Now here, now let's apply it to this case. I'm just trying to make sure I'm getting a different color. Here, I can simply say f of s comma t becomes u0, right? And a is 0 and b is h of x. Okay, so I simply have d by dx of 0 to h of x u0 dt is simply, please let me know if you notice a mistake in any of this. Okay, 0 to h of x del by del x u0. Here t becomes y. Okay, so this is u0 of x comma y. That's what it is. Okay, y comma t as well, but t is a dummy variable for us. Okay. Okay, so this will be dx, sorry, dy. What am I doing here? I'm doing an integration from, okay, this will be dy. Okay, dt becomes dy. So s becomes x and t becomes y. That's the idea. Okay. Plus u0 and of x comma h of x d by dx of h of x of h That's this term here. This should be simply 0. All right. So I'm interested in this quantity here. That is integral of 0 to h del by del x of u0 of dy is simply d by dx 0 to h of x u0. This is sorry, dt becomes dy u0 dy, correct, minus u0 of hx. Okay, so I clearly seem to have missed this term here. Yeah. Let's put that in. Let's put that in. What do I get now? This
Sir,
is
here
simply-
u0 at y equal to h now, sir.
Yeah, this is u0 at y equal to h. Okay. Yeah. So this is d by dx of whatever I've already written down here, which is I'll simply copy it from here. I'll copy these terms because these seem to be correct. Correct? There's no question about them, right?
Yes, sir.
I've not made any silly mistakes here. So let me just copy them here. Okay. And let me also erase this part here. Okay. So far, okay. So this is the first term. Right? This is just this quantity here. Okay. Minus u0 of hx. u0 is simply what for us? Del p by del x. Del p0 by del x of y square by 2 minus h square. Of y square by 2 minus hy evaluated at y equals h multiplied by hx. Okay, so I just have to add this to the previous one. This will become del p0 by del x y square by 2 minus hy. That is h square by 2 minus h square. That will be minus h square by 2 times hx. Okay. Okay. So now I need to substitute. This is my expression. And finally, let's also evaluate the first one in the integral. That will be del square p0 by del x square h cube y cube by 3, that is h cube by 6 minus x square by 2. What happens here? By del x into minus hx into h square by 2. And this fellow finally becomes plus, correct? This is an
Yes,
extra
sir.
term that we have. Plus del p0 by del x times h square over 2 multiplied by hx. This is the last one. So let me just highlight the corresponding terms. This term here is this one. This whole thing here. This whole thing here is are these two. So far, okay, guys?
Yes, sir.
Okay, so now I can clearly see that these terms are getting cancelled. The second and the third term, right?
No, sir, they are added now, sir.
Oh, sorry, they are added. I'm sorry. Okay, they get added. Yeah. So this becomes del square p0 by del x square. this becomes h cubed by 6. I think there's a mistake here somewhere here. I forgot an h. I forgot an h. Okay. H cubed by 6 minus h cubed by 2. That is minus h cubed by 3. Correct? This becomes plus del p0 by del x into hx multiplied by h square. That's all it is. Just added, as you one of you pointed out correctly. So I have simply have 0 to h del by del x of u0. This is dy. This is what we have evaluated. So I think this deserves to go into a box. Let's put that in a box so that we won't make a mistake. Okay. But so now that we have evaluated this, I have now substituting. This is what I'm writing down now. Now the top of the line on the screen that you see here is a substituting del u0 by del x dy integral 0 to h in the kinematic condition we get. Okay, so what we will do, I'll do here is I will simply, oh, this is a challenge for me. Okay, let me just do one thing. Let me move this down. Okay, in fact, what I will do further now is I'll be creating space. Okay, so the idea is that this fellow here, what you guys have pointed out, this is clearly having an error. Okay, this is also incorrect, this is incorrect, this is incorrect. Okay, I have already, this is what we worked out now, just now. So now substituting here, now I'll stick to the color. What's the kinematic condition? We should be substituting. Our kinematic condition was this one that I've highlighted in blue here. 0 to h. Let's, for the sake of discussion, let's copy it there. Okay, this is my equation, right? And this simply gives me I've evaluated 0 to h. That is del square p0 by del x square minus h cubed by 3. And then I have plus hx times h square. This is the first term plus del h by del t plus u0. What was u0 again? It is del p0 by del x times h square over 2 minus hy evaluated at y equal to h. Okay, correct? Multiplied by hx. This is 0. Okay, and they simply get minus del p0 by del x h cubed by 3 plus del p0 by del x hx h square plus del h by del t, and this gives me h square minus h square by 2 minus h square, that is minus h square by 2 plus del p0 by del x multiplied by minus h square by 2 and hx is equal to 0. Now, instead of these two fellows cancelling out, I'm still a little concerned about it, where this is going. But till I've done this, I don't want to.
Sir, here dou square p0 by dou x square plus first.
Oh, sorry. Thanks, for. This becomes minus, correct? No, this becomes plus. Okay, that's a bit concerning. Have I missed something here? Looks okay so far. Uh-huh. This is what I really have. There's something not right. I made some mistake here, algebraic mistake. Let me just see. So far, okay, this option in blue is the right one. Let's go over to that's X. I have a suspicion that there is a mistake in this integration by parts. Let me just check this here. Mm, Oh, there's a this is okay. I think I've noticed a mistake here, one more mistake. I assume that this you guys said you tried out this term, right? Shouldn't there be a plus here? Shouldn't there be a plus here?
Yes, sir. Yes, sir.
Hmm?
Yes, sir.
Okay, so that is a plus here as well. Okay,
Yes, sir.
so these terms actually don't add up, they cancel out each other, right?
Yes, sir.
So this doesn't exist.
Just come down the way.
So far, okay?
Yes, sir.
Okay, so here what I've done is I've taken the derivative inside and I've taken what is it called? Derivative of A times B. That's what I've done here. So I have the derivative of the first term, then this is one, and over here it is the first term and the derivative of this. Derivative of this is just minus hx. But I have an addition here, plus here. So this box here that I gave should actually be just this term. Now this fellow goes into the, where does it go here? I start substituting. Okay. Okay. So I have now realized that this flow doesn't exist. Okay, which means that this doesn't exist. So this becomes a minus sign. Okay, and this becomes a plus sign. I think that's all right.
Yes, sir.
Okay. And if this becomes a plus sign, this is exactly what I have over here. If you see the one that I'm highlighting in the box now, and the one that was written, I'm highlighting in yellow down right below. Okay, let me just highlight with. These two are exactly the same. You see that? The top and the bottom. Let me make that a little smaller. And therefore, the equation is still all right. Equation J is now all right. Himanshu, are you there?
Yes, sir, I'm there, sir. Your voice is not clearly.
Did you see the mistake that was there? I've identified the mistake, but the final equation is still correct. Hello?
Sir, your voice is not clear, sir.
Voice is
Maybe
not-
internet connection problem from my side.
Okay, so, okay, can you see the screen?
Yes, sir, I can see the screen, sir.
Okay, let me just type what I have to say. I have to figure out how to chat. How do I chat? Okay, I have a chatting here. I'm just chatting here.
Now I can listen, sir. Now I can hear this.
So you see the issue, you said you derived this equation, right? This integral itself was wrong. The one I've highlighted in yellow, right? The yellow braces below, yellow bracket, flower brackets below. You see those terms here? That is basically that there should be a plus over here. The mistake was the one I'm highlighting in yellow. This should have been a plus. In my original derivation, what you notice is this is actually not a plus, but a minus.
Oh, okay. Now I see, sir. Now
That is where the issue is. The issue did not come from the. So I basically was a little careless over there. Okay. And when I work out, the final equation is still correct. Equation J is still correct. There's nothing wrong with that. Okay.
Okay, sir. I got it. Good.
Okay. So Sham has asked, but I don't know if Sham is still there. Sham, are you there? Okay, Sham left, unfortunately. The pattern of the final exam will be very similar to the assignments, except that now we have, I mean, it's actually, you by the end of the course, you'll see 12 assignments. Okay. And those 12 assignments are objective type questions. Each assignment has questions ranging from maybe anywhere from a minimum of 6 questions to a maximum of maybe 12 or 13 questions, I guess, in an assignment. So the final exam also will be similar, but the exam will have about, I think, maybe around 40 questions, and it will be you'll be getting 3 full hours to write, and it will have questions which are similar to the assignments. Okay. So if you work out the note, if you go through the entire material and go through the go through all the assignments on your own, then I think you will be fine. Okay. So any questions? Okay. So finally we get equation P naught for P naught, and after that we can now basically take the expression for disjoining pressure. I have a brief discussion of where does disjoining pressure come from. This is basically van der Waals forces, and these are intermolecular forces. but the challenge is to incorporate these intermolecular forces in a macroscopic system. So of course, these forces, because they are intermolecular forces in nature, and these are what we can refer to as fluctuating dipole forces. These forces will only arise when the thin films are really thin. Okay, and but once you and what we are also doing is we are incorporating it as an additional pressure term. Okay, and so once we do that, then we can finally get the dispersion relation, which is, I believe, this is the dispersion relation. Yeah. So I see a new student here, Pratiparna Das. Hi there. But I just want to just point out that it really gives me a lot of pleasure. It gives me a lot of happiness that some of you actually have worked out these derivations on your own. I mean, and in the process, highlight these things, because I sort of know that this final equation is correct. Okay, I worked on these kinds of problems in my research, sort of know that this equation J is correct. So I was fairly confident. Of course, the challenge is, of course, to debug where the mistake has come from. Typically, it's a sign error from some silly mistake. But I'm very pleased that some of you have actually gone ahead and worked out these derivations on your own, rather than just putting blind faith on my derivation.
Excuse me, sir. I wanted to ask something. Hello.
Yeah, I can hear you.
Sir, this really baffles me a bit, because when we were talking about van der Waals force, it is a force which is existing in some I mean the range of that force is, as I read in a book, it was somewhere around 10 to the power -7 or -8. That is the place where van der Waals forces start showing their effect. But when we are talking about the thin films, that is not that thin. So the question is, I mean, but we were saying that van der Waals forces are so mathematically we can say, but intuitively it does not come very obvious, because so a force which is in the range of 10 to the power 7, 10 to the -8, it starts dominating there. So I mean, how even you said in that that when the D, the separation distance, which we were talking about in the why the van der Waals force comes at the first place. So the question is that I mean, when the forces are existent in that small separation distance, then how can they cause rupture of that film? Mathematically it's okay, but intuitively it does not seem very obvious.
Okay, so let me rephrase parts of your question so that we are all clear about what we're talking about. What you were saying is that what I must have mentioned is that these van der Waals forces become important only in micron and submicron thin films. That's what you mean by 10 power 6 or 10 power 7. We are talking about the thickness of the film in meters, correct?
Yes.
So you're talking about thick films of the order of 100 nanometers. So I'll give you a context. Okay. So the tear film on the eye is about 5 microns. That's on the higher side. Okay, around 5 microns is the tear film, thickness of the tear film, or even smaller. If you make a soap bubble, a large enough soap bubble, the thickness of the bubble is usually of the order of a micron, a few microns. Okay. But on the soap bubble, you actually have a large variations of the thickness. Now, these variations in thicknesses can come from a variety of sources. Okay. One of the reasons why you have variations in thickness is because if you create a soap bubble in the air, you have air currents around the bubble, which will disturb the bubble. Okay, and that will make the fluid on the bubble flow, and that leads to thickness variations. And these thickness variations are indirectly visible to the naked eye through these fringes that you see. If you basically make a soap bubble in just in daylight, you will actually see a rainbow color. Okay, you'll see all the visible colors of light because there is actually a different wavelengths are actually scattering at different angles, and that is what is giving you these fringes that you see. Okay, right? So what I'm trying to first tell you is that it is true that there are thickness variations on the thin film. Now, just because you make a soap bubble doesn't mean it will rupture. It will take some time. There is a certain time scale after which it will rupture. And if you do very careful experiments, then there is a drainage of the thin film. The same thing would happen to the thin film that drains out. So what we are really trying to do in this calculation is we are saying that drainage occurs. The drainage occurs because of other forces, like mainly gravity, correct? Right. You could also have drainage because of forcibly driving fluid from one place to another by introducing a shear flow. By blowing air on the bubble, you could actually make the fluid move from one place to another. But if you create a soap bubble and leave it in the air, it's likely to drain because of gravity. The same is true for the TO film. If you actually go to a doctor and want to get tested for the dry eye disease, one of the things that the doctor does is to keep your eyes open and looks for drain and waits till the thin film ruptures, the tear film on the eye ruptures. It has been shown, it has been discussed extensively that the tear film on the eye is actually a complex tear film. It has just over the cornea of the eye, there is a thin layer of a highly viscous fluid called mucins. Okay, this mucin layer is typically of the order of 0.5 microns or less. We are talking about films of the order of only hundreds of nanometers. Okay, and that thin film, once it ruptures because of van der Waals forces, the tear film itself will rupture. Okay, this is one of the main theories, leading theories for how the tear film ruptures. So, and you can lay down a thin film on a plate, on a horizontal plate. That the moment you lay down a thin film on a horizontal plate, what really happens is there will be certain portions where the thin film can become really, really thin. And that is where rupture eventually happens. There is no direct mechanism for surface tension and viscous forces to cause rupture. Okay. I'm not suggesting that this is the only mechanism for rupture. We are looking at, in fact, if you look at the lecture, this is the entire lecture has focused on van der Waals driven rupture of thin films. Is this clear? Surface tension will try to flatten the interface. Viscosity can only retard the flow, but it really cannot completely suppress the rupture once van der Waals forces become dominant.
Okay, I got it.
So the moment you create a thin film, which is, if it's fairly thick, okay, several microns, okay, thick or millimeters, it is not going to rupture by van der Waals forces. Okay, if that was your doubt, it will not rupture by van der Waals forces. You will need some other mechanism to create local spots in the thin film where the thin film is really thin. And there, van der Waals forces become important.
Yes, actually, that was what I was thinking. So that I was thinking the thickness of the film meant to be like millimeters, but now it turns out like if it is millimeters, then it won't be because of van der Waals. I mean, not.
If you introduce a millimeter size thin film on a plate, then it will still rupture by van der Waals, but then the film will not rupture from at t equal to 0, rupture doesn't occur. If that was the case, you will never be able to create thin films at all. What you really need to do is once you create this thin film, there could be other processes become important, which causes the thin film to locally thin. You could have local hotspots where you have evaporation, okay, or you could have Marangoni effects which drive fluid away from certain regions and create local uh, dipping of the film. It could be a variety of reasons, but once you have that, then this theory becomes applicable.
Yes, sir. Now got it. Got it.
Okay.
Got this, sir. Now. Yes.
All right. Okay. So if there are no more questions, I think we'll call it a day. Thanks for
Sir,
your questions. Yeah,
sorry, sir.
you have a question?
Sorry, sir. Just interrupting this. In the rupture of thin films, part 3, I wanted to ask that when we were writing, sir, in where we have written this expression, where eta dimensional eta is equals to beta times exponential iota k, that part, sir. When
Maybe
we
it's
have,
not 3, maybe it's 4.
I think I've actually read, I've not written the lecture number, but yeah, around that only.
This
yes,
one,
yes.
eta of x comma t is beta times this. Yeah.
Sir, that omega that we were saying here, sir, actually omega, whenever we have referred in the lecture previously, that omega has been the complex omega. So
Yeah.
shouldn't there be iota kx minus omega t? So I is outside in this, where just below the line we have written linear PD. So that omega, wherever here we have written earlier, it was complex omega. So there should not be I. So I should be like with kx, right? Not with omega t. I omega t.
No. You could have omega. You can have an I in front of omega. I mean, if omega is okay, let me just write this. If omega is a complex number, I'll erase this, but I'll just write it for your for explanation. If omega is a complex number, okay, meaning it belongs to the complex set, which means that omega is omega r plus I omega I, then I omega also is a complex number, right? In general. That is, I omega is simply I omega r minus omega I. This is also a complex number. This is also of the form A plus IB.
Yes, sir. It is, but just in that convention that we were following earlier. So earlier we have written I. So just I thought like.
So you could write it in several ways. You could write this. This is called normal mode form. I may have mentioned this in the course. This normal mode form, there are several ways to write it. You can just simply say eta is beta e power I kx minus omega t, or eta is beta e power I kx plus omega t. This is also perfectly all right. The only difference is when two people have done this omega calculations with using two different forms, these are solution forms that you're assuming, remember. So if you compare, if two people do it, let's say Himanshu and Sai do it with one does it, let's say with minus omega t, the other one does it with plus omega t, then you cannot directly compare your results unless you recognize that your real part is of opposite sign. Or your real and imaginary parts will change sign. Okay, you have to be clear about that. This is, you can also write it as eta is beta e power I kx plus omega t, but you can recognize that omega is a complex number, or eta is beta e power I kx minus omega t. All of them are valid. The only difference is you are interchanging the real and imaginary part, including their signs between these different conventions. There
Yes,
isn't
sir.
anything like one is correct and the other is not.
Yes, sir.
They're
Yes,
all,
sir. I,
you can choose anything you like. Sometimes
Uh.
I myself sometimes do it as in the first form. Sometimes I do it in this form, depending on many times the mood and how you do it and what context you do it. Okay.
yes, sir. Yes, sir. I get it, sir. I get it.
In this case, the clear film basically will not really travel any further. Right. Meaning this will not be a traveling film. A traveling film, if I write it in the way that I've written in the omega form, traveling part will be associated with the imaginary part or imaginary part of this exponential term, which is in this case it will be omega r because there is an I sitting in front. But omega r, I believe we'll get it to be 0. Because if you have a thin film, physically, if you think of a thin film on a plate, there is no reason for, if you generate a small wave, there is no reason for, in this case, a wave to spontaneously move to the left or right. Okay. There are waves, there are sometimes you will get problems where you will spontaneously get waves which travel to the left or right. Like, for example, if you throw a stone on the surface of water, you will see that the wave can travel left and right. In fact, it will travel both. And if you do it in an unbounded horizontal film, the waves will travel in radial direction in all directions. Okay.
Yeah, I get it, sir. I get it. Just two more quick questions I have.
Yeah, sure.
Sir, in the fourth part of the last lecture, where we have stopped, you wrote for one by c bar equals to 0. That fourth part. Yes, here actually there was 1 by c bar is equals to 0, where you have said that s equals to a bar minus g bar by 3. That part. Where we have neglected the. So you said that we should do it ourselves. So we did. That was the only expression that you asked us to derive. It was c bar equals to 0. C bar inverse equals to 0.
Okay. Capital number is 0.
Yes, capital number is 0. Yes.
Okay.
So, sir, there you have actually there, sir. When we put the expression of a bar minus b bar by 3, and we say that it will be unstable if a bar is greater than b bar by 3. So, when we put the expression, there is no lambda which is coming out there. So, we cannot. I cannot really make out that as to. I mean, what does it tell us? Because we were at the end of the day, we were concerned about what would be the lambda.
So
If you
these
could
are here. Okay, let me understand. Here, what you're trying to say is what you're trying to determine is the criteria for instability.
Yes, yes, sir.
Okay.
Hmm.
So if you for example if you have a criteria like this that we have here, then the thin film is unstable. So it's not very. I'm not able to fully understand what you're trying to say here.
When we were trying to derive this expression for instability, sir, so everywhere we were interested in knowing what would be the lambda above which it would be unstable. So, like we have derived everywhere. So, in that expression where we have c bar, I mean the capitalized number is 0. In that expression, if you put a bar is greater than b bar by 3, which is instability, which would make the film unstable, there would be no.
Hold on a
There
sec.
would be.
Yeah, but let's. So if you notice here, okay. So no, if you notice here, what I've really done is the expression that I've taken for eta is beta into e power x ix. There is no k there. Correct.
Yes, sir. There's no k
So,
there.
yeah, what I'm trying to look at is, okay, that may have led to some confusion. So what I would encourage you to do this is, okay, let me tell you what is the context in which I had done this, and let me just see how we have done this.
Here in this fourth part, we have this fourth
So
part.
here you see, okay, no, this part, if you see here, the way we have essentially done is you have e power, eta is beta times e power I kx minus omega t. That part is okay. The first term below this word linear PDE.
Yes, that is okay.
Then what I'm essentially doing then is I am basically simply rescaling the length, horizontal length in terms of the wavelength. Okay, for horizontal length, it is basically the wavelength, and the vertical length is basically thickness h naught. So eta scales like eta tilde is like eta times h naught, and k times x bar will give me x. K tilde x tilde gives me x. So in other words, what I've really done is I've done it in a non-dimensional form. That's why there is a wavelength, but this wavelength is unity. The reason it's unity is because everything is scaled with respect to that wavelength. So you could, I would encourage you to do the following. I mean, this can be sometimes confusing. So you can do the following. You don't do this at all, what I've done. You simply start with eta going like x tilde y tilde. You assume to start with this linear PD. And just like we have done the analysis for the Rayleigh plateau instability, you assume a normal form just like this, what I've given you. Beta is e power I kx minus omega t. And you will get a wavelength, you will get information in terms of wave number or wavelength. Okay. So again, instability depends on the thickness again. Okay. So you will not be able to create, you will end up still getting the same criteria. Okay. You will still, the physics will still not change. This criteria star that I have got here. Okay, the dispersion relation, sorry, that I've got here, from which I can look at the various criteria, I can derive various criteria. This dispersion relation will still be the same. But if you do the whole process, you'll still see that this dispersion relation will resemble this and can be reduced to the equation star. You understand? So I would encourage you to try and repeat the same exercise and follow the same kind of analysis that we've done for Rayleigh plateau. Don't assume that the wavelength is unity. Actually, this is a non-dimensional wavelength. I have basically rescaled horizontal x in terms of the wavelength. Okay. Are you there, Himanshu?
I'm there, sir. But I'm okay.
So you start with this linear PD. You start with this linear PD that I've shown here, and let's go back to the analysis that we've done for Rayleigh plateau. If you look at the analysis for Rayleigh plateau, what we again got was something like this. We have this equation. We have again 3 linear PDs. Okay. You can, of course, you can combine them into a single PD if you want, but let's stick to these 3 linear PDs and assume a normal mode form. In this case, the normal mode form is slightly different. You see, it's e power I k z plus omega t. Okay. Now, you can assume a similar form and do the analysis. So you can assume e power I k x plus omega t and do the analysis and get the dispersion relation. And you'll see that the dispersion relation that we've got here will be similar to the dispersion relation that we've got right here on the screen. You can reduce, they won't be exactly the same. One can be reduced to the other by again non-dimensionalization. Or rescaling. Okay.
I'll go through this. Sir. I'll go through.
Yes. So, in fact, I believe I shared some paper. Did I share the paper? I showed some paper in the last meeting, right?
Yes, sir. I saw the 2 papers.
I believe in those papers you will find a wave number present in those research papers.
So the paper of Ajay, no, or the JFM paper.
Yeah, in fact, I've in all those papers you should find a wave number present. The normal
Yes,
mode
sir,
form, the normal mode form is not like the one that is shown here. Okay. Right. Any other questions?
not from my side, sir. I'm clear.
So we'll call it a day then. All right.
Okay, sir. Okay, sir. Thank you, sir.
Thanks a lot for joining. I'm very grateful to some of you to point out the typographical errors and the calculation errors. But I'm also while it does please me that some of you have taken the effort to calculate these terms and verify these things on your own. And that is the best way to learn, to do it yourself. Okay. And I'm glad you are doing the right things. Yeah, but of course, I'm also pleased that there isn't really um, uh, an error in the rest of the lecture. If the original PD was faulty, then of course the entire lecture would have been in jeopardy. So thankfully, equation J is all right. All right. Okay. So with this, we'll stop the live session and then we will. I'll see you all next week again.
Thank you, sir.
Thank you. Can I request the NPTEL team to stop the live streaming?